This question says, list the intervals on which f is increasing. So when I look at a graph to decide whether a function is increasing, decreasing, or constant, what I want to do is I want to trace the graph moving from left to right. So starting on the leftmost part of the graph, I'm going to trace. And as I trace, I'm taking note of what's happening to the y values. So I'll start, and we'll label it after we go through the whole picture. So starting from the left, as I trace, my y values are decreasing. Then I get to this minimum value, and then the y values are increasing. Even though there's a point marked here, that doesn't change that the y values are increasing. Then we get to this value here, and now the y values are decreasing. Now increasing, and then decreasing, and then increasing. So now let's label that. So starting from the left, my y values are decreasing along this section. They're decreasing along this section, and decreasing along this section. I'll use a different color to indicate that it's increasing along this section, increasing along this section, and increasing along this section. So we've identified the portion where the graph is increasing, but now we need to write down the intervals or list the intervals. Now the intervals that we list, those are going to be our x intervals. So we're starting at -8 and ending at -2 for this section. That's -8 to -2. And some books use a definition on an open interval, and some books use an interval that's a closed interval. So sometimes you'll see it written as the open interval like this, and other times a closed interval like this. For this section here, our x values are 0, and that x value is 2. So that interval goes from 0 to 2 if we use open intervals, 0 to 2 for closed intervals. For this section, our x would be 5 and 7. So that interval is 5 to 7 or 5 to 7, depending on the definition. So to list the intervals where the function is increasing, that would be -8 to -2, 0 to 2, 5 to 7. If we're dealing with open intervals, -8 to -2, 0 to 2, 5 to 7 for closed intervals. List the values of x at which f has a local maximum. What are these local maximum if they exist? When we're looking for local maximum, we're looking for peaks in the graph like this. This particular graph has 2 of them. For the local maximum, maximum would be the highest y value, and local maximum is the highest y value in a local area. So if we can narrow our focus down to a nearby area, we can see very clearly that this is the highest y value in the nearby area. So the x value that matches would be at -4. We have another local maximum if we narrow our focus to this local area. We do have a highest y value, and that occurs at an x value of 12. And what are these local maxima? So these y values occur at, looks like 16 for both of them. So I like to say it as we have a local max of 16 at x equals -4, and we have another local max of 16 at x equals 12. Find the average rate of change of f of x equals 3x squared plus 4 from 1 to 3, from -2 to 0, from -2 to 1. So the average rate of change is very similar to the slope, except when you're finding the slope, you're finding it a slope of a line, and we're finding the slope of 2 points on this curve. So the average rate of change formula is going to be f of b minus f of a over b minus a. And you can see that's the same as our slope formula that we use y2 minus y1 over x2 minus x1. So a and b are our x values, and then f of a and f of b are our y values. So starting with part A, it says from 1 to 3, that's telling us that A is 1 and B is 3. So we need to calculate f of A, f of 1, and also f of 3 before we can calculate the average rate of change. So f of 1 would be 3 times 1 squared plus 4. That's 3 times 1 plus 4, which is 3 plus 4, and that's 7. F of 3 would be 3 times 3 squared plus 4. 3 squared is 9. 3 times 9 is 27. And 27 plus 4 would be 31. So now we can calculate that average rate of change, f of b minus f of a over b minus a. That's 31 minus 7 over 3 minus 1. And 31 minus 7 would be 24. 3 minus 1 is 2. And so we have an average rate of change of 12 from 1 to 3. So we'll do the same thing with part B. We want to find the average rate of change from A equals -2 to B equals 0. So we need to calculate f of -2. That's 3 times -2 squared plus 4. -2 squared is 4. 3 times 4 is 12. And 12 plus 4 is 16. Then we'll calculate f of 0. 3 times 0 squared plus 4 is 4. So using the average rate of change formula, that's f of b minus f of a over b minus a. We have 4 minus 16 over 0 minus -2. 4 minus 16 is -12, and 0 minus a negative is 0 plus 2, and that's 2. And -12 over 2 is -6. So the average rate of change from -2 to 0 is -6. So then we'll do our last one, part C. We're going to do from the average rate of change from A equals -2 to B equals 1. We've already calculated f of -2 a moment ago. That's 16. And we've already calculated f of 1. We did that earlier over here. That's 7. So we'll find the average rate of change, f of b minus f of a over b minus a. That's 7 minus 16 over 1 minus negative 2. And 7 minus 16 would be negative 9. 1 minus negative 2, that's 1 plus 2, that's 3. So we get negative 3. The average rate of change from negative 2 to 1 is negative 3. For the function f of x equals 4x plus 6, express the slope of the secant line in terms of x and h. And then we have some other parts there, but we'll wait on that. What I want to do is talk about the secant line first. I want to give you an idea what the secant line is. So a secant line is when you have a curve, let's say this curve here, and you're going to choose 2 points on that curve, and then draw a line connecting those 2 points. So that line that's connecting those 2 points, that is the secant line. The secant line is a line that passes through 2 points on the curve. So what we want to do is we want to find the slope of that line. So let me show you how we'll express that line. We're going to say that we have this first point being x, f of x. That's an x and a y value. I've used x and f of x because it could be any point on that line. And then a small distance away from that point, so if we're thinking on our x scale here, this is at a value of x, a small distance away from that point, that small distance is h. So this other x value will be x plus h, x plus the small distance. Then the y value at that point, so here's our y scale, the y value at that point will be f at that x value, x plus h. So we're going to be able to find the slope of the secant line by using our normal slope formula. Our normal slope formula is to take y2 minus y1 over x2 minus x1, except we're going to use these ordered pairs that we have here. So the one ordered pair is x f of x, and the other ordered pair is x plus h and f of x plus h. So we'll use for y2 f of x plus h, for y1 f of x, for x2 that's x plus h, and for x1 that's x. And with a little bit of simplifying in the denominator, we get f of x plus h minus f of x over h. So this is the formula that we're going to use to calculate the slope of the secant line. And you may also be familiar with this because this is the formula for the difference quotient. So for part A, let's find the slope of the secant line. So f of x plus h would be 4 times x plus h plus 6. Let me give myself a little bit more space. It's 4 times x plus h plus 6 minus f of x, so that's minus 4x plus 6 all over h. I'll use the distributive property on this 4, and I'll also use the distributive property on this negative. So I have 4x plus 4h plus 6 minus 4x minus 6 over h. The 4x and 4x cancel, the plus 6 and minus 6 cancel, leaving me with 4h in the numerator and h in the denominator. Those h's cancel, leaving me with 4. So the slope of the secant line is 4, and that's a constant. Now, with a little bit of thinking about this, it makes sense that that slope is a constant, because f of x equals 4x plus 6 is a straight line. It has a y-intercept at 6 and a slope of 4. So if we take 2 points, any 2 points on this line, and try to draw a secant line, we're going to end up with the slope that is the same as the slope of the original line. So because our function f of x is a straight line, the slope of the secant line is a constant. But if our function were a curve instead of a straight line, then our slope would be changing. The slope of the secant line would change based on the points that you choose. For part B, it says find the slope of the secant line for h equals 0.5, 0.1, 0.01 at x equals 1. So this is a unique problem because our slope of the secant line that we found is a constant 4. So it's not dependent on what h is, and it's not dependent on what x is. So the slope of the secant line is going to be 4 for each one of these situations. So the value of the slope as h approaches 0 will be 4. For part C, find the equation of the secant line at x equals 1 with h equals 0.01. So to find the equation, we need to know the slope and a point on the line. So we already know the slope is 4. The slope of the secant line is 4. And we want to find the point where x equals 1. If x equals 1, f of 1 is 4 times 1 plus 6. And that's 4 plus 6, which is 10. So I'll find the equation of the line using the point-slope form. Y minus y1 equals m times x minus x1. So I'm using that point, 1, 10. So in for y1 is 10, in for the slope is 4, and in for x1 is 1. That's y minus 10 equals 4x minus 4. I'll add 10 to both sides, and I have y equals 4x plus 6. So the equation of the secant line is 4x plus 6. So finally, I'll graph the original function, 4x plus 6, as well as the secant line, 4x plus 6, in the same viewing window. And we see that the two are actually the same lines. So this happens because our original function is a straight line, and because of that, the secant line is the same as that function. A linear function is given. Complete parts A through D. So our linear function is h of x equals 1/4 x minus 4. In part A, we want to determine the slope and the y-intercept. So we know that this function is in slope-intercept form, y equals mx plus b. So the slope is 1/4 and the y-intercept is -4. Then we're going to use the slope and the y-intercept to graph the linear function. So we have a slope of -4 and a y-intercept of -4, and the slope is 1/4, so I'm going to rise 1 and run 4 and connect those 2 points with a straight line. Then we want to determine the average rate of change of the function. So there's a theorem that says if you have a linear function, then the average rate of change is the slope. So the average rate of change is the slope, which is 1/4. Then it says to determine whether the linear function is increasing, decreasing, or constant. If we look at this graph, if we trace it from left to right, the y values are increasing. But we can also tell that this function is increasing based on the value of the slope. Whenever the slope is positive, we have an increasing function. Whenever the slope is negative, you have decreasing function. And if the slope is 0, you have a constant function. So this is something that works for linear functions. So for this example, we have our function h of x increasing.